In this video, we're going to talk about time division multiplexing, or TDM. So what exactly is TDM? TDM, or time division multiplexing, is a communications process that transmits two or more streaming digital signals over a common channel. It is also known as a digital circuit switch. In TDM, incoming signals are divided into equal fixed-length time slots. After multiplexing, these signals are transmitted over a shared medium or channel and reassembled into their original format after the multiplexing. The main application of TDM is to transmit or receive different data and signal using a common single transmission line. TDM is used to transmit and receive huge amount of independent data over a single line. The first TDM was developed for telegraphy application. Using this system, multiple data transmission were routed over a single transmission line. Nowadays, TDM is used for many applications. Here are some of the applications of TDM. 1. For digital mixing system. A digital mixing system or digital mixing console is an electronic device used to combine, route, and change the dynamics and other properties of multiple audio input signals. TDM is also applied to pulse code modulation transmission system or PCM. A pulse code modulation is a method that is used to convert an analog signal into a digital signal so that a modified analog signal can be transmitted through digital communication network. Another is for optical data transmission system or optical fiber communication. For landline phone system, Global System for Mobile Communication Technology or GSM, for satellite access system, and for cellular radio. TDM has some advantages and disadvantages. Here are the main advantages of a TDM. Hardware required for TDM is very less. TDM circuits are not so complex than other systems. This is a huge plus for TDMs. In TDM system, the full bandwidth of a channel can be used. TDM provides more throughput than FDM or frequency division multiplexing. Another great advantage of TDM is that it is mainly used for digital signals, but it can also be used for analog signals. TDM system does not need any carrier wave or carrier signal, while FDM needs a carrier signal. There's no intermodulation distortion. TDM needs synchronization, while FDM does not need synchronization. Another noticeable disadvantage is it provides less latency than FDM. Latency refers to how much it takes for a signal to travel to its own end back. Although lower latency is better, since latency is essentially a delay between when you take an action and when you see the result. High latency is when it takes longer to see the results. The less delay, the better. This may either be an advantage or a disadvantage for a TDM. In TDM, address information and buffer is needed. Synchronous and the synchronous time division multiplexing are techniques that allow multiple signals to be sent over a single faster connection by sectioning a link into time slots. Each source signal uses the channel for a limited period of time. They are intended to increase bandwidth utilization of high-speed links and enable multiple slower links to simultaneously use a single faster connection. Synchronous and asynchronous TDM are highly useful technologies for transmitting digital signals more efficiently. But what are synchronous and asynchronous TDM exactly? In synchronous TDM, time slots are fixed, while in asynchronous, time slots are flexible. Synchronous has fast transmission, while asynchronous has slower transmission. Synchronous needs common clock signal, while in asynchronous, there is no clock sharing. Synchronous may have to wait briefly until data can be sent, while in asynchronous, it can transmit when it's ready.
A digital multiplex hierarchy is a hierarchy consisting of an ordered repetition of tandem digital multiplexers that produce signals of successively higher data rates at each level of the hierarchy. It may be implemented in many different configurations depending on the number of the channels desired, the signaling system to be used, and the bitrate allowed by the communications media. There are two of the hierarchies, namely Plesiochronous digital hierarchy and the Synchronous digital hierarchy. The Plesiochronous digital hierarchy was designed to transport huge amounts of data over digital equipment such as fiber optic systems. The bit streams from different sources are not guaranteed to have exactly the same timing. Even though the nominal bitrate is the same, this is due to the fact that each piece of exchange equipment uses its own internal clock for timing purposes. Although these clocks are extremely accurate, they are not synchronized, and there will be enough difference in the actual bit rates of the tributaries feeding into a given multiplexing level to require some additional overhead in order to provide the necessary synchronization. It also has a high cost of transmission and complex multiplexing method, which involves bit stuffing, wherein it is the process of inserting non-information bits into data to break up bit patterns to affect the synchronous transmission of information. Since there is a growing demand for more bandwidth, it meant that more stages of multiplexing were needed throughout the world. In order to meet the demand, the digital multiplex hierarchy evolved in various parts of the world but differing with one another. It was developed and adopted by Europe, North America, and Japan using different tributaries for multiplexing and demultiplexing. In Europe, PDH adopts bit rates starting with the basic multiplex rate of 2048 kilobits per second with further stages of 8, 34, and 140 megabits per second. The basic digital multiplexing standard established in the United States has a primary rate of 1,544 kilobits per second. This basic rate is also being followed by Canada and Japan, but Japan has slight deviations at higher order multiplexing and demultiplexing levels. Here are the limitations of the PDH. The maximum capacity for PDH is at 566 megabits per second, which is limited in bandwidth. As mentioned earlier, multiplexing and demultiplexing is very complex since different frame is used for transmission and in data layer. Since every other manufacturer has its own standards and PDH also has different hierarchies, it is difficult to integrate interconnecting networks together. Now, for the synchronous digital hierarchy. Synchronous digital hierarchy is an international standard for high-speed telecommunication over optical and electrical networks. It was developed and launched to replace PDH systems and eliminate synchronization issues for bulk telephone and data exchanges, as well as increase data transfer rates and provide a simpler, more flexible network infrastructure based on the optical fibers. It also would operate a new multiplexing method which would be synchronous and based on byte interleaving. This means that SDH has extremely precise timings. SDH uses a basic rate and all are based on multiples of 4. Digital services. Digital services are categorized into 3: teleservices, bearer services, and supplementary services. Teleservices. Among ISDN or Integrated Services Digital Network teleservices are telephony, teletext, telefax, videotext, telex, and teleconferencing. They can be provided using circuit switch, packet switch, frame switch, or cell switch networks. Bearer services. It is a transfer of information between users without the network manipulating the content of the information is provided by the bearer network. Reverse charging, call waiting, and message handling are examples of supplementary services which are all familiar with today's telephone company services.
A quick introduction to the Ethernet. Ethernet is the traditional technology for connecting devices in a wired local area network, or wide area. Simply, it refers to the most common type of local area network. Usually, Ethernet speed clocked at only 10 Mbps. Fast Ethernet goes up to 100 Mbps, and today's Gigabyte Ethernet supports 1000 Mbps. Cables run from modem or modem router combo to the Ethernet ports on your online-enabled system. What Ethernet is not, though, is wireless. When it comes to technology, most business organizations will certainly look at few important factors before making a decision. Some of these important factors are cost-effectiveness, scalability, reliability, availability, technical and customer support services from the service provider, and the specific advantages and disadvantages that each technology has. One of the most commonly made comparisons when it comes to the internet connectivity is that of T-line versus E-line. It is true that both of these technologies are predominantly used for voice and internet connectivity. Therefore, it is indeed useful to check out a few aspects which are common to the both of them. It is important to know their hardware and how they work. When looking into the question of T-line versus E-line, it is useful to begin with how they operate. A T-line is a dedicated line which runs from business organizations to the telecom company's office. This dedicated line is capable of delivering 1.5 Mbps transmission speed. Normally, a T-line is made up of copper lines or fiber optic cables. Conventionally speaking, Ethernet is capable of being deployed only within business organizations' network. However, today, plenty of service providers are offering it across wider geographical locations and even giving global access. Normally, Ethernet services can be deployed within a minimum speed of 10 Mbps. Depending on the service that you require, it can even go upwards of 1 GB per second. Scalability. This is a huge criterion when it comes to T1 versus Ethernet. Even though standalone T1 line is capable of giving you 1.5 Mbps, carriers can also give you something known as bonded T1 lines. Depending on the number of bonds, you can enjoy greater speeds. For example, with 6 bonded T1 lines, you can get 9 Mbps. While Ethernet service, as stated before, can come with a minimum speed of 10 Mbps. And because it is easily scalable, you can enjoy higher bandwidth as well. Cost factors. Obviously, for any business organizations, discussions about T1 versus Ethernet will also have to do with budgets. Generally speaking, the cost per meg for Ethernet services is lower than T1 lines. This is because the equipment and cables that are required for Ethernet services are inexpensive. Based on what enterprises are paying, net of discounts and deals, We've seen monthly bills for 10 Mbps Ethernet Metroland service for less than $240 per site in one US city and more than $1,900 in another. Installation is also less expensive, and the overall cost of price structure is also more competitive than T1. However, an Ethernet line may turn out to be more expensive in a direct comparison depending on the area and the amount of work required for a build-out. A T1 line might cost between $1,000 to $1,500 per month, depending on who provides it and where it goes. Performance. While both these connections perform at really high levels, a T1 line comes out marginally better when you compare T1 versus Ethernet across the performance criteria. This is because a T1 line is capable of providing always-on internet access. This is backed up by a robust service level agreement which can guarantee customers a specific time frame for repairs and a guarantee of performance as well. Thus, when it comes to T1 versus Ethernet, a business organization can easily look at cost and performance factors and then decide between the two. Ethernet circuits are used by business to provide reliable, dedicated Ethernet connections for internet access as well as other applications including email, file sharing, web hosting, data backup, video, or VPN access, unlike in TDM connection. Overall, the Ethernet is more popular because of its balance with service speed, reasonable costs, easy installation, support various network protocols, and wide acceptance in computer marketplace.